Welcome back. So this time I want to talk about what this term scalable means. We made the point that working with really large data is an important aspect of data science, and we've mentioned the word scalability before. We haven't talked about really what that might mean. So a couple of different ways to think about it that I want to talk about here on this slide are here. So, operationally and in the past, one way to think about this was, look, it needs to work on data that doesn't fit in main memory on a single machine. Okay. So maybe you still only have one machine to work with, but this means that if it can, you need to be able to bring data off of disk in pieces, operate on it, and then maybe write it out in pieces. Okay. And so a bundle of algorithms that could work on data in this fashion by bringing in data piece by piece to memory, such that the memory footprint at any given point was small. This is something the databases provided. Right? So you could write a query, and you knew for sure that it was going to finish as long as the data was there on disk, and you had sort of a minimal amount of memory, at least to get started. Okay, but and I might use the term out of core processing here. So out of core means it uses the disk to operate. So in core means everything you're doing fits entirely in main memory. Out of core means you need to sort of work with the disk appropriately. And so databases were the database community were specialists at out of core processing of large data sets. But increasingly, this notion of scalability wasn't really enough. Okay, and so you saw this pretty acutely with websites that were coming online in the 2000s, where one big server, no matter how big you bought that server, you couldn't bring data off of disk fast enough to meet all the requests, and so you had to start being sure that things were in memory, and the only way to do that is start adding more machines. Okay. And so increasingly, especially, Google especially is sort of known for this, although many of the large media companies do this, is that scalable really kind of means being able to use up to thousands or maybe even more, tens of thousands of cheap computers and apply them all to the same problem. And so we might call this scale out, while getting bigger and bigger and bigger main memory and more cores perhaps would be scale up. Okay. Fine. So another way of looking at this that maybe is a little bit more precise is to think about this kind of in terms of algorithmic complexity that you may or may not be familiar with depending on how much computer science you've taken. But let me give you just a flavor of what's going on here. So in the past, you might call an algorithm scalable if given in data items, your algorithm does no more than n to the m operations on it. Okay, so this may be m may be 1, in which case it's a linear time algorithm, or it may be 2, in which case it's a quadratic time algorithm, and so on. But this was deemed tractable, right? And so you'd prove properties about you would prove that you could find a polynomial time algorithm to solve some problem, and it was sort of thought to be scalable, or assumed, assumed. That was the definition of what scalable was. Things that were non-polynomial that took more than this, for example, exponential, where you might have m to the n, were exponential time algorithms, and they grew much, much faster, and they didn't scale. Okay. But this isn't a very tight bound on scalability in practice, right? A quadratic time algorithm may be sort of feasible. You start getting into the fourth and so forth, it becomes pretty difficult to do for very large data sets. Okay, so now you would say that it really can't just be n to the m. It's got to be n to the m over k, for some pretty large k. So you have to have a lot of k being the number of computers you can apply to the problem. And so you have to come up with an algorithm that can really exploit this properly. Okay. And then one more point that I'm going to make now, but we're not going to return to in this segment, but I hope to at the end of the course, is that it could be that soon even this isn't good enough. And for in data items, you really should do no more than in log n operations. And so the in here means for every data item that comes in over the wire. So this is applicable to sort of streaming applications. And the data is coming in so fast that you only get one pass at it. So for every operation I have, I'm allowed to process that data item, and then I'm allowed to put it in some sort of an index, and that's this log in factor. Okay, and so whenever you see log, you should think trees. So I'm allowed to take each item, inspect it, and work with it, and then stick it into some tree data structure. But that might be about it. It's just too big to make multiple passes at. Okay. And so examples of this might be this large synoptic survey telescope that we heard about. They're taking sort of 30 terabytes a night. You can't sort of make too many passes on this data at one time. Okay. And so this whole area we think of as streaming data, which I guess I have written here, but I'll write it again. And we'll come back to some of the techniques for dealing with big data in a streaming context. Okay, so fine. So two different views of what scalable might mean, and we're going to talk in this segment to give you some examples and some intuition for this. Can we make use of lots of computers and this in over K? Okay. All right, so here's a little example problem that's admittedly somewhat oversimplified. So we want to find all the matching DNA sequences where a set of sequences is a short string consisting of the letters G, A, T, and C, and you're given a short sequence, and you want to find all the ones that just exactly match that. Okay, so find me all the sequences that are exactly equal to this one that you're given. So how might you do this? Well, with this little cartoon, imagine that each one of these black lines is a sequence. Right, so this black line corresponds to this sequence, and this black line corresponds to this sequence, and all the other black lines are other sequences. And, think to yourself for a minute, propose an algorithm to find sequences matching your target sequence. Okay. Well, making no assumptions about the data whatsoever, it's just given to you as a list. One thing you can do is do sort of a linear search. And so we're going to inspect the first item, and we're going to compare it to our target sequence. And if they're equal, great, we found one. And if they're not equal, what do we do? Well, we move on to the next one. So this is not equal, and this all happens at time equals 0. And then we move on to the next one. And so at time equals 1, we check another sequence and compare it for equality. And if it doesn't match, we keep moving on. And so on and so on until we get to time 17, where we find a match. And here I've said contains instead of equal. I guess I changed the meaning here. But so yes, we found a match and we send it to the output. Okay. So how long does this take? How many operations do we do? Well, we did 40 records. We were given 40 records in this cartoon, and we made 40 comparisons. And so within records and in comparisons, we say that the algorithmic complexity is order n. Okay, so this is a linear time algorithm for this simple search and retrieval task. So the question is, can we do any better? And if you've had some experience thinking about data structures, taking some data structures classes, you should be thinking, yes, we can. All right. So one way to do this is to sort the sequences. So how does this help? Well, certainly we could still do the linear time algorithm and inspect these guys one at a time. But we can also do something a little bit smarter. What if we start in the middle? So start in the middle and compare our target sequence to the sequence we found here, and they're not equal, but we can see that this one that we found is less than our target sequence. Okay, so we know that the sequence we're on is to the left of our target sequence. We know the target sequence is to the right. Right? It must be somewhere in this direction. So we've just removed the need to check half of the data, right? 20 records. Okay, so now jump to the middle of this guy and compare again. And now we see that, well, boy, we overshot. This one is greater than this one. Well, once again, let's see. Here we've removed half of these guys on the first step, and here we've removed half of these guys. And now we know it's in this range. Skip to the half again and compare this one, and now it's less than, so we're sort of bouncing back and forth around our target. Let's see if I can draw this a little better than I did. Cross those out. Cross those out. Now cross these out. And so we know it's somewhere on this side. And in the next step, we find a match. Okay, and here if we have multiple copies of the same item, we know that they'll appear next to each other, so we could just walk through the records, gathering up all the ones that match if we needed to. Okay, so how long did this take? Well, here we still had 40 records, but we only made 4 comparisons, right? So within records, we made login comparisons. We navigated this sort of implicit binary tree. We did a binary search over this sorted data, okay? And so this lookup was order login. Now, we did have to sort the data ahead of time, and if you have to include that, then that's an in-login operation that we're not going to necessarily talk about. But once you have that sorted data available to you, it's now, it only takes login operations. And so this is perhaps far better scalability. All right. And this is a good trick, and it's such a good trick that it's been baked into many systems, especially, I'll argue, relational databases. And we made this point before, but I want to make it again, is that databases are good at these kinds of needle in the haystack problems, right? Extracting small results from big data sets. They can transparently provide this sort of old style of scalability. What I mean by old style scalability is that fits in main memory, as we've said a couple of times. Your query will always finish regardless of the size of your main memory. In addition, it makes an excellent sort of index platform, a platform for building and using and reusing indexes. Okay. So relational databases are good at this old style scalability in the sense of out-of-core algorithms, and they're also good at this old style scalability in the sense of finding logs, right? Finding logarithmic time algorithms. Okay. So indexes are easily built and automatically used when appropriate. And we've talked a little bit about this during relational databases. You can write a single statement, create index, give it a name on a table and a column name, and it will sort records according to that column. Now, the actual data on disk may or may not be physically sorted depending on the details of which system you're using and how this is working. And typically in this statement, it would not actually be moving the physical records around, but it would build an auxiliary index. But regardless, you get to take advantage of this logarithmic time access pattern. Okay, and so just by writing this one statement in one line of code, you can create the index and take advantage of it. Okay. And then every query that comes afterward that needs to use that would benefit from using that index, is able to. The optimizer automatically selects the correct index if it's appropriate to use. So this is much easier than you having to sort of rewrite your code by hand in order to either make it out of core, right, or to take advantage of an index. Okay, so when you're comparing relational databases to, say, scripts in R or scripts in Python, there's a lot of algorithmic work that's already been done for you that you're getting for free just by turning your problem into a SQL statement. Okay. Fine. So you're, buying into a lot of code if you can tie one arm behind your back and write it as a SQL statement. It's not just SQL versus a much more expressive language like code. You're actually getting a lot of benefit out of doing so. Okay. So let's look at another task called read trimming. So here we're given the same set of DNA sequences, but instead of searching for one particular sequence, we're going to trim the final few base pairs from each sequence. Okay, so we're going to trim off a suffix and return the data set where each read is now just a prefix of a former read. Okay, so fine. So how do we do this? Oh, and the reason why you need to trim off the suffix, this actually comes up in practice, and the reason is that the accuracy of the sequencer drops off fairly abruptly after a certain length of read, and trimming off the last several base pairs from every single read is kind of a standard pre-processing operation. Okay. Fine. So how do we do this? Well, we can do the same trick that we tried the first time with the search task, meaning that we can process each record in turn one at a time. Right? So at time 0, we can trim off the suffix here and just return TACCT, and at time 1, we can trim off this suffix and so on, and at time 17, there's our old friend that begins with GATTA, and so on. But here, unlike the search task, there's no index that's really going to help us, right? We have to touch every single record and manipulate it, right? We have to take a prefix from it and remove the suffix. And so the operation is fundamentally order in, right? There's not going to be an algorithm that is less than order in, right? You have to at least touch every single record. Okay, but can we do any better? Well, yeah, right? Processing the first task is completely independent from processing the last task, which is completely independent from processing this task. Well, I keep saying task, processing the record. Okay. So while there's no index, we can break this data set into pieces and process each piece independently. Okay. So imagine we take our single data set and break it into these chunks and assign each chunk to a different machine, or maybe a different processor to be a little bit more general. Now at time 0, we can process one sequence from each chunk all at the same time, and at time 1 we process the second sequence from each chunk all at the same time, and so on. And so here, how much work did we do? Well, we did the same amount of work. We still processed all 40 records, but how much time did it take? Well, it only took 7, I say cycles here, 7 time units to be a little more general, because we were given these 6 workers. And so the complexity here is n over k, right? For every item we can divide, we do on average, for n items we do in over k time steps we're completed the work. Okay. Last time we talked about scalability, and we argued that scalability really means working in parallel. And we talked about this specific task, which is, read trimming. Okay, so this is a bunch of small genetic sequences, and your task was to trim off the last few characters from each one. Okay, and we sort of showed that this is pretty simple to think about in parallel. You would divide the set of reads into chunks and put them all on separate computers, and process them all in parallel. Here, there's a function f that takes a single read and trims off the last few characters and returns the prefix. And you can apply this function in parallel, and you can get out the data set you want, which is a set of trimmed reads. Okay, so let's see some more examples. So a new task that was actually needed to be performed at the New York Times in 2008, and they have a couple of blog posts about it that you can read, was, in a simplified version, was to convert a bunch of TIFF images into a different format. And what was really going on here is that they had digitized images from the newspaper along with some information about the optical character recognition, so some extracted text, and they wanted to turn this into a more web-friendly format. And so they had to convert the images to a web-friendly format, and they also had to convert the extracted text into a little package of JavaScript code. Okay, so they're going to get ready to put this stuff on the web. All right, so this is 405,000 images, which was quite a bit, especially at the time. Okay, but the schematic looks sort of similar, right? You take a big set of TIFF images and you split them into chunks and put them on a bunch of different computers, and you have a function f that converts a TIFF to a PNG and does the other work too, let's say. And what you get out is the data set you want, a bunch of PNG images. Okay, and they're distributed across these machines. Fine. So let's look at another example. All right, so now we want to run thousands of little simulations, and what we have are the parameters to each one of those thousands of simulations. And so an example of this at the URL here at the bottom of the slide is from simulating muscle dynamics, and this comes up a lot. You have these Monte Carlo simulations that need to do they understand sort of phenomenon stochastically by running lots and lots and lots of simulations with different kinds of different inputs and then kind of averaging the results, okay, as opposed to modeling everything precisely. So now you want to run thousands of simulations. Well, you have a set of inputs, of parameters to these simulations, and you break them into chunks and put them all on separate machines and apply the function, and here the function is actually running the simulation, and what you get out is the output of the simulation distributed across all of the machines. Okay, so this, a pattern should be emerging here, right? So another example. So imagine each one of these little bars is a document, and your task is just to find the most common word in every individual document. Okay, well, same thing, distribute the documents across the K computers, and then your function f now in this case opens up a single document, figures out which word is the most common in that document, right? And just produces that word. And so now you have a big distributed list of pairs where, the first part of the pair is the document ID and the second one is the word. Okay, so that could be useful, but it's a bit contrived. consider a slightly more general program that computes the word frequency of every word still in a single document, right? So instead of just finding the most common one and producing that, now you're going to produce a histogram of the frequencies of every word in the document. Okay, so given this input, you produce all of these items, right? A set of items. And the only reason I'm making this distinction from the last one is that the last one, took a single document and produced a single word. Now we're taking a single. I just want to make it clear that that's allowed. Okay. Oops, the animation isn't here, but I don't think I'll bother fixing it. So you have millions of documents. You distribute them again. Now your function returns a set of word frequency pairs, right? But that's okay. And now we have, lots of little lines here, each line representing a single word, let's say. So they're not one-to-one anymore. But that's no problem. The function just returns a set of things. All right. So fine. So there should be a pattern here, right? We have a function that maps a read to a trim read. We have a function that maps a TIFF image to a PNG image. A function that maps a set of parameters to the simulation result, right? It's the simulation itself. We have a function that maps a document to its most common word. And we have a function that maps a document to the histogram of its word frequencies. Okay. So good. So these kinds of tasks we think we know how to do in parallel. Given a big set of objects and a function that knows how to process a single object, you should be able to think about how to parallelize this, right? I didn't give you a treat, but we can abstractly understand how this is done, right? So let's say that one more time. We have a big set of objects. We have a function that maps a single object pile of computers, right? The objects among the computers and the function f in parallel. This is trivial. All right. Okay, so what if we want to compute the word frequency across all documents, not just a set of frequencies for each document, or the frequencies for a single document? Okay, so here, if we have these three documents, now we want to get a single histogram that counts up the number of times the word people appears across all three of them, and the number of times the word government appears across all three of them, and so on. So let's go back to our schematic here, the pattern. Well, now we want to compute the word frequency across 5 million documents, and we can still distribute them among k computers. So far, so good. And then for each document, we return a set of word frequency pairs, and now I've switched the notation here from f to map, since we can consider this a map. That's the terminology I used. Okay, but now what do we do? Right, so what we could get out here, what we will get out here is a set of frequencies, but that's not what we want. We want a one big histogram. And to build this one big histogram, we have to make sure that a single computer has access to every occurrence of some particular term. So if the word history appears in some document on this machine, and it appears, twice in this document and 3 times and two times in documents on that machine, and so on, we have to sort of group those all up and send them to a single place just so we can count them. Okay. So let's look at this again. So if we distribute the documents across these computers, we apply our map function to each document in order to produce a set of word frequency pairs, and now we have a big distributed list of these sets of word frequencies. And now we want to get these workers involved in the process. And these guys are going to be the ones who count the occurrences of a particular word. Okay. And so imagine all these little colored red lines are occurrences of words, such that all the red lines represent a single word, occurrences of a single word, and all the green lines represent a different word, and so on. Well, so these guys are going to get sent to their respective locations, so such that this worker is in charge of handling all the occurrences of the blue word, and this worker is in charge of handling all the occurrences of the red word, and so on. Okay, so now instead of lines that go, from 1 to 1, we have lines that go from this one computer to a bunch of different computers. Okay, and so on, right? So you have to sort of shuffle the data, we have to spray this data out across the network. in order to regroup it now. Fine. So now that we have the data grouped the way we want and partitioned the right way, we can apply another function, which I'll call the reduce function, which in this case it does something very simple. It just counts them. And that allows us to produce our final result, which is, oh, there are 4 green words and 4 red words and 3 blue words, and so on. Okay. So now the schematic looks a little different. We have a sort of a two-step process. So we start with some large set of objects distributed over a bunch of machines, and then we want to apply some function f to each one of those objects, and that was our first step. But then the output of those functions are all going to be redistributed across the network and grouped to form groups. Okay. And then the second step is to process each one of those groups. So I'll write, instead of f, I'll write map here, and I'll write reduce here. Okay. And so that's exactly what MapReduce does, and we'll explain this in more detail next time. But the key idea here is that the user, the programmer, is going to write these two functions, a map function and a reduce function, which are serial. And what I mean by serial is they're not parallel. You don't have to worry about how to manage, how to program a distributed cluster within each one of these functions. You just write a function map that takes in an object of some kind and returns some other object. And I'm not using object in this sort of object-oriented sense here. It's just sort of in the mathematical sense, just any sort of input to produce any kind of output. Okay. And then the reduce function takes a set of objects, which I'll note this way, and returns some other kind of object. And actually this can be a set of objects as well. And in fact this can be a set of objects as well. So maybe I'll switch colors here. This can actually be a set of things, and this could actually be a set of things. So for example, we saw a document returning a set of word frequency pairs. But you can think of it, it's not necessarily important to understand what's going on here. Okay, so this is an interesting hypothesis, right? That perhaps all distributed algorithms can be expressed as sequences of these two-step operations, right? A map followed by a reduce, and then maybe more MapReduce, MapReduce, MapReduce as needed. Okay, and we'll talk about that in more detail next time. So last time we talked about parallel processing as a lead up to MapReduce, and we ended up with this schematic here in the context of this example where we're counting words across a set of documents, which is sort of the canonical example to start thinking about programming in MapReduce. And so each one of these vertical black lines represented a document, and we split them into smaller sets and sent each one of those sets to a separate machine. And then we applied our map function to each one of those documents in turn. And so if the map function, if you recall, took a single document and produced a set of pairs, and each pair was a word along with a count of the number of occurrences of that word in that document. Variations on this that you can imagine. Okay. Now, this word may have appeared in multiple documents, one here, one on this machine, one on this machine, and so on. And so now we need to group them all together onto a single machine so that we can count them. And that's exactly what this shuffle phase did. Okay. So here I've written 4 different tasks, processing, sort of looking like it's processing a single group at a time. But, I want you to think about how many map tasks are we going to have and how many reduce tasks are we going to have. Well, the map tasks are 1 per document. We have to call the map function. How many invocations of the map functions are going to be? Well, we're going to call it once per document. How many invocations of the reduce function are going to be? Well, it's the number of groups that are produced by the output of the map function. In this case, it's once per unique word appearing in any document. Okay, and so in some sense, the number of machines we need to apply to this problem is maybe kind of predictable in the map phase. It's corresponds to the size of the input data set, which we presume to know. But the number of reducers we're going to need is maybe not known ahead of time, right? It depends on the size of the map output. Here we might be able to reason about it because we maybe know how many words there are in the English language, and we can assume that with a big enough set, all of those words will be represented at least once. But in general, it's dependent on the output of the map, so you don't really know. Okay, and so the only point I want to make is that we made a decision here to draw it as 4 different machines, but it may, it may be the same 6 machines you use the map phase, it may be 1,000 machines, and so on. Nothing's stopping you from sending all of the word occurrences to a single machine and having this one machine process the green group, then process the red group, then process the blue group, and so on. Or maybe you would do 4 at a time because there's 4 cores in the machine. Okay. But that wouldn't be as, perhaps as efficient because it would be doing a lot of serial work. At the other extreme, you might think, well, we're going to need millions of tasks. Let's allocate, hundreds of thousands of machines to process them so that each machine is doing very little work. Okay. And that might make sense, but then the trade-off is perhaps sort of spinning up all these machines and preparing them to do the work. Okay. So there's a decision to make there, and we'll come back to that. Okay. But let's talk a little more about MapReduce itself. This is, I'm belaboring this for a reason, because what I want you to do is start thinking in terms of MapReduce. Every problem you have, think, what if the data set was absolutely enormous, way too big for one machine? How are we going to split it into pieces? And a very good way of thinking about how to split things into pieces is to think about how you'd write a MapReduce program to do whatever it is you're trying to do. And so this is, yet again, the same example, just drawn a different way. So here, the input is document ID followed by a value, and the value here is the entire text of the document. And the map function, just to make this clear, produces a set of things, not just one thing. Then they're shuffled to produce this. So this is word 1 with a count of 1, word 2 with a count of 1, word 3 with a count of 1, and so on. And then on the other side, what we get is word 1 with a group of all the occurrences, 1, 1, 1, 1, 1, 1, 1, 1, 1. And then finally, the reduce function counts them all up and finds that there's 25 occurrences. Okay. So I'm probably, I guess if this is completely obvious, you can always fast forward. I guess one of the beauties of doing this online. Okay. So fine. So what is MapReduce? Well, that's the programming model we just described. And there's a paper in 2004 that's on the reading list that describes this. And there's a couple of key motivations for doing this in that paper that I think sometimes get lost when you hear about the popularity of MapReduce today. And we'll talk about those two benefits in a moment. So one thing to realize is that MapReduce refers to the abstraction, and it's the name given to it by the authors of this 2004 paper. Hadoop is an implementation of MapReduce that came a few years later and was written by some people at Yahoo originally and then became an open source product that is managed by Apache and has lots of contributors. Okay, so the key idea for MapReduce was really this programming model, which it says here, right? Now it had a system with it as well, but the programming model being able to express lots of different tasks and have some sort of implementation automatically turn that into a parallel job turned out to be pretty powerful, right? This was an attractive way to write parallel programs, again, because you didn't actually have to worry about the parallel. All you did was write a serial map function and a serial reduce function, and the parallelism happened for free. And so the evidence that this is not so much about the system as it is the programming model is that you see MapReduce implementations appear in other contexts. There's people who have implemented MapReduce over GPUs. There's people who have implemented MapReduce on multi-core machines in shared memory. There's people who have implemented MapReduce on high-performance computing platforms, on groups of mobile phones, and so on. Okay. So this goes back to one of the motivations for this course, where I want to focus on abstractions where possible as opposed to tools. And so we're talking about MapReduce, the programming model, but we'll spend a little bit less time on the specific implementation, Hadoop, although you will have a chance in an optional assignment to work with Hadoop directly. Okay. So fine, so what is the data model of MapReduce? It's this bag of key value pairs. What I mean by bag is a set that might have duplicates in it.
right? And so we've seen that before. The document ID with the value, that's a key value pair. Sometimes on the input, we'll be a little sloppy and not worry about precisely what the key and the value is. For example, if you're just given a record, you can assume that it's, say, the entire record is the key, okay? Or a document, sometimes even, we may not have a explicit document ID, but you can assume the URL or the file name or something is the key. The output of the mapper, though, the distinction between key and value gets really, really important because that's what controls the shuffle, as we've seen in that example. Okay. And so both the data model here is all about key value pairs, and the input is going to be a set of key value pairs, and the output is going to be a set of key value pairs. And the point is that the set of key value pairs can get arbitrarily large, right? We're going to be able to process this set no matter how big they get. There is kind of an implicit assumption that the key and the value are small. And small here doesn't necessarily mean very, very small. It just means that it needs to fit on one machine. There's no support for if value grows to be terabytes, it's not going to work. And so a document fits on one machine. That's okay. You know, an image fits on one machine, and so on. Okay. So fine. So the map phase, as we've said, you provide a map function. The input is an input key and an input value, and the output is a bag of intermediate keys and values. It doesn't have to just produce, take in a single input and produce a single output. It can produce a set of things. And we saw this with the word count example. A single document came in, but a set of things came out. That's okay. All right. And then the reduce phase, what you're given is the intermediate key. This will be the same intermediate key that was produced by the map phase, right? One instance of the same intermediate key produced by the map phase. And then a bag of values that were associated with that intermediate key. And they may have, and the important thing here is that they may have come from any mapper whatsoever. The grouping into this bag of everything that shares the same intermediate key is handled automatically by the system. So the system will group all pairs with the same intermediate key and then pass that bag of values to the reduce function. And the implementation details of whether this is actually handed to you as a bag or whether it's an iterator, if you're familiar with that term, that you can step over, is implementation dependent, but it's not important to think about. It's a collection of values. Okay. Fine. So here it is all in one slide. The map function takes a in key and an in value and produces a list, a bag of out key intermediate value pairs, and the reduce takes an out key and a list of intermediate values and produces a list of out values. I don't think I like this slide. I think I prefer the earlier one. The one thing I will mention is that the terms map and reduce, I tried to motivate that in the last segment, where you can think about converting a TIFF image to a PNG image. You can think about mapping a function that maps every TIFF image into some PNG image. And that's where the term came from. And if you look back, this kind of came from the functional programming community. They use these terms. It doesn't precisely mean the same thing, but it's inspired by that. Okay. All right. So here's maybe the implementation for the example we have. And a lot of times what I like to do is sort of ask you to pause and think and stare at this code for a little bit and think about what it does. Here we've kind of gone through the example a lot, so I'll reveal the secret. But it's still instructive to work through this for a moment yourself. And in fact, maybe I'll end this segment there, and you can stare at this and make sure that you understand what it does. Okay, last time we talked about MapReduce and gave the abstraction and went through some examples. And we ended up on this slide, which is maybe the first time we've seen pseudocode or any kind of code that actually implements these map and reduce functions. And so I asked you to sort of take a look at this. Actually, at the end of the last segment, there are a couple of mistakes that I've fixed in this slide. So you can compare the two and see if you can figure out what the mistakes are and why I changed them. Okay, so let's walk through this. So what does this code do? Well, as I sort of gave away last time, this implements this word count application that we went through schematically, with cartoons, and this is the pseudocode that actually implements that. or an example of pseudocode that could implement that. You can't execute this code since it is just pseudocode. So what are we looking at here? Well, the input, as we said, the data model of MapReduce is key-value pairs, and so the input is going to be a big set of key-value pairs, and the map function is going to operate on one of these key-value pairs. And in this case, the key is the document name, and the value is the document contents. So it could be a big string, right? It maybe comes from a PDF file or a text file or a web page or whatever. Okay, and so this code is pretty simple. It says, well, for each word W in the input value, so this sort of assumes that somehow you can iterate over all the words in the input value in the text of the document without really specifying how. Then emit a key-value pair where the key is this first element, which is the word, and the value is the number 1. Okay. Then the magic shuffle phase takes over and groups all the key value pairs that share the same key into a single group. And so all the occurrences of a particular word will show up as a group. And how that group is represented is as a key along with what we've called here an iterator over the intermediate values. And if you're not familiar with the term iterator, you can think of this as just a collection of values. Okay, so as an example here, if you have the word, the map function will produce pairs like this. Every time it sees the word history in any document, it'll produce this. And then finally, on the reduce side, you'll have the word history here and a sequence of number 1s. Okay, and so what does this code do? Well, it initializes a final result to 0, and then it says for each value in this list of intermediate values, add that value to the result. And so here we just add them all up. And then finally we emit a final key value pair, which is the intermediate key, the word itself, and the final result. And so maybe the output here is, history 25. And we walked through this a couple different times, so I'm hoping this is pretty clear by now. Now, I claim that without changing this reduce function at all, you could make a change to this map function and get a significantly faster algorithm for computing this. So I want you to think for a second about how that might be done. So the thing to look at here is that, oh, goodness, we're emitting a key value. Well, I gotta stop resting my hand on this. We're emitting a key value pair once for every occurrence of a particular word. And each one of those key value pairs has to be shuffled across the network and sent to the reducer. So if we see the word history 25 times in a single document, we're going to emit 25 key value pairs for that word, and they're all going to get grouped up by the shuffle phase. But we have access to the entire document here in the map, in this map function. So why not pre-count all the occurrences of those words and produce a different key value pair right? Which means the word history appeared 25 times in this particular document I'm processing. And so now, I shouldn't have said 25. Sorry, that's confusing. That's confusing. I didn't mean to make the same number as this. This is, in our previous formulation of this problem, it turned out that we said that the word history appeared 25 times across all documents. And I shouldn't use the same number up here because that's pretty confusing. So let me change that. So here we say the word history appears 5 times in this particular document, and it appears other times in other documents. Okay. So now we have only one key value pair emerging from this document for the word history as opposed to 5 different ones. And overall, across all the documents, across all the computers being applied to this problem, that's a significant savings. Okay,
And then, double check to make sure that you don't have to change this code here, but, you hopefully it's clear that you don't, because you're adding the total value into the result. And so here, instead of adding the number 1 5 times, well, sorry, 25 times, I guess, in the reduce side, you're adding it some number of fewer times, right? You're adding 5 plus 10 plus 3 plus 4 and so on to get 25. Okay, so this loop is evaluated fewer times. Okay, so the reason I want to go through that example is to demonstrate that, there's two things. One is to try to think in terms of MapReduce and think about how you can cast a problem as operating on a bunch of chunks, emitting keys to define groups, and then operating on those groups. But also that, you actually have a lot of control over the performance of these algorithms by just modifying the map and reduce functions, right? So even though you aren't working on the system internals, you only have these 2 points of control, you can actually get very different algorithms, very different behavior, and different amounts of intermediate results being created, and so on, just with these two functions. And so you want to get a feel for not just how to express it in MapReduce naively, but also get a feel for how to do things reasonably efficiently. And in fact, this example sort of demonstrates one of the things you're going to be looking for is the bottleneck often, not always, is the amount of data going across the network. And so if you can reduce the amount of output produced by the mappers, especially in terms of number of key value pairs, you'll tend to improve performance. Again, not always. And we'll see some more examples of this. Okay, so I'm going to stop there, and in the next segment we'll go through a variation of this problem that has similar characteristics, but really just to drive home how to design these MapReduce algorithms on slightly variant problems. Okay, so let's talk about another example that is sort of similar to this very simple word count example, but has a slight change. Okay, so now we want to maybe know the makeup of a corpus of documents, a set of documents, and try to understand the characteristics of the word length. And so now instead of a histogram on word usage, we're going to group things by the length of the word. Okay, so we want to know how many words have greater than 10 characters and so on. All right. So, here we might group words into big words, medium, small words, and tiny words, where the big words are everything that's 10 plus letters, and the medium words are in red here, and they're everything from 5 to 9 letters, and so on. And you could define your own sort of bucketing scheme, or just not even try to bucket them and use the exact number. Okay. So, what we're basically showing here. So I'm hoping that some of you are already kind of seeing how this is a essentially trivial variant of what we already just did. And this is one of the points I want to make is that you'll see these patterns in designing MapReduce algorithms come up again and again. And so once you start to get a feel for how to do it, it won't be that every new problem looks different. But the other thing that's nice about maybe the next few slides, I think, is that it shows a little bit more detail in how these things are broken up. So for example, if this is a document, what we hear, I guess the point I want to make is that before we sort of assume that every document was a small thing, but it's not impossible that you might have one document that's very, very, very large. This typically wouldn't happen with a document for various reasons, but imagine these weren't just documents, but these were just big data sets of words. And so every document itself, an individual document may be so large that it can't be processed by a single map function at a time. And so the question is, are we stuck here? Is the MapReduce framework broken and it's going to crash? And the answer is no. What will happen is when you load this large document into the system supporting MapReduce, and we'll talk a little bit more about what this lower level system is, what I mean by loading, the file system underneath MapReduce, underneath implementations of MapReduce. when you do that loading, the file, the data set, the file, will automatically be split into chunks. And so we can pretend that this document was so large that it needed to be split into chunks. Okay. And so chunk 1 is this top part, and chunk 2 is this small part. Now, if a small document is underneath the chunk size, then it won't get split, but a large document will. Okay. And so this could have happened with the word count example too. This is not something specific to word length, obviously, but it's another twist that we're exploring. Okay. So fine. So now this top chunk gets assigned to map task 1, and it produces this little histogram of the counts of yellow words, red words, blue words, and pink words. And we can imagine, you should think about how the code might look if you were to if you had to write this, right? You would need to take the link, iterate over all the words in the document just like we did before. But now instead of emitting a key being the word itself, you would count its length and put in a case statement and figure out what color it is in this notation, and add that to a count. Okay. Fine. So the output is these 4 key value pairs. And in chunk 2, we do the same thing and produce a different set of 4 key value pairs. Then in the shuffle step, all the yellow key value pairs will be grouped together, and there's 2 of them, and all the red ones will be grouped together, and so on. And then in the reduce phase, you'll add these 2 numbers together to produce 37. Okay. So the structure here is really identical to word count. It's just basically a change to the map function. And in fact, in this case, you could actually literally use the exact same reduce function. Right? For every key, add up all the contributions of it. You wouldn't need to change reduce at all. And this is something else you'll see, is that certain functions are more general than others, and you'll reuse them time and again. For example, counting things and adding things up is pretty common in these MapReduce algorithms, and so general reduce functions that add things and count things come up time and again. Okay, fine. So word count, generally the canonical place to start when thinking about MapReduce. Word length, very minor variation on that. So let's think of another sort of minor variation on that, and this one arguably is even simpler than word count. So here we want to build an inverted index, and what an inverted index is when you have a corpus of documents, you can presumably efficiently access any given document by its name, right? So if you want to look up a URL on the web, you can do so. But for a search engine, a very primitive search engine, you might want to look up documents that contain a particular word. And so building this index to support word lookup to provide a list of document IDs that contain that word is called an inverted index, and it's one of the primitive steps in doing any kind of text retrieval kind of system. Okay, so now imagine we just had tweets instead of documents, and the input here is that the keys are these tweet IDs that I've invented, and the value is the text of the tweet itself. And so the desired output here is the word along with a collection of tweet IDs. Okay. So how do we do this? Well, again, the code is actually simpler than it was before, because now on the reduce phase, instead of, we'll think about it for a moment. The map phase, instead of producing each word pancake in 1 for an occurrence, we won't do that. Instead, we'll put out pancake and the document ID itself, right? And all of these guys will be produced. And so this tweet 1, the map task that processes this tweet 1 will put out pancake tweet 1, love tweet 1, and so on. Okay. Further, an optimization here is
if you see the word, I guess I should have had an example of this in here, but if you see the word pancake twice in the same tweet, do you need to put it out, do you need to omit the key value pair twice? Probably not to build this index, because all you're trying to record is that the tweet contains the word pancake, not that it, not how many times it appears. So fine, so these key value pairs get shuffled across the network. And now the reduce task, what does it do? Well, it's going to get a key, pancakes, this should have an S on it, I guess, and it's going to have an iterator over all the document IDs that contain pancakes, which in this case is tweet 1 and tweet 2. So do we need to do any processing on this key and group of values? The answer in this case is no. The reduce function is complete, is non-existent. There's nothing to do, right? When the group is exactly what you want in this case. And this pattern actually shows up somewhat often as well, where you do want the map and you do want the shuffle phase to do the grouping, but all you wanted to do is to perform the grouping. You didn't actually care about the reduce function. So you're not counting these things, you're not adding them up in any way, you're not doing any processing on the tweets, you just want to omit that. And that's perfectly fine, because this group of values is perfectly serviceable as a value itself. Okay. So if you are used to, say, relational databases, nested structures, collections of values within a single cell in a table, in a single row, are generally disallowed, right? And this is actually first normal form, if you're familiar with that. But here we don't care. It's any key and any value. A key can have substructure and a value can have substructure. Okay, fine. So that's how to build an inverted index in MapReduce. Let me stop there, and next time we'll talk about this relational join example. So this will be how to implement a join from a relational database as a MapReduce program.
So let's look at an example that doesn't involve processing a corpus of documents. So let's think about how to implement the join operation that we learned from the relational algebra in MapReduce. Okay, so here recall that you're given two relations, and a relation is a set of tuples, right? And you're trying to find every record in one relation that corresponds to a record in the other relation, right? And so here we're going to join on SSN equal to imp SSN. And actually, it wasn't quite correct for me to leave this unspecified. There's a notion of a natural join that would match it up if the field names, if the attribute names match, but here they don't, and so I need to be explicit about what I'm joining on. Okay, and so the output here is these three records. Okay, this record joins with these two, and this record joins with this one. Fine. Now, imagine that both of these relations are huge. Okay. So the map phase here is going to process every tuple in general. And we have a problem right off the bat that join is a binary operation, right? It has two input relations. The left relation and the right relation. You're trying to find corresponding tuples in one and that match the other. But MapReduce is a unary operation. It processes a single data set. So how can you, to a first approximation, you can't express join in MapReduce, period. But that's okay. There's a bit of a trick here, and the trick is, look, it's okay that imagine the data set here is just a big jumble of tuples. It doesn't matter what table they came from. We just lump them all together into a single data set called tuples. Okay, and that'll be what we process with MapReduce. Okay, and so here I'm asking the question, what is this for? Well, this is a label that we've attached to every tuple so that we can know where it came from, and we'll see how that's used later. Okay. Now, I'm not being specific about where you get this label or how you do it in MapReduce, but I want you to think logically that it's necessary. And in practice, it's not that difficult, right? Because for example, if you're processing, you have distributed files from this directory representing all the employee chunks, and you've got distributed files in this directory representing the assigned departments chunks, you can look at the file name to tell what table it is. And so in the map function that you write, you can determine that, aha, this has file name, this has the employee relation name in its file path, and I'm going to go ahead and attach that as part of the record. Okay. And so we could write pseudocode for this, and in fact you might as part of the an upcoming assignment. All right. So fine. So what's the map phrase look like of this relational join? Well, for every record on the input, you're going to produce a key value pair. We know we have to produce key value pairs because that's how MapReduce works. So what's the key going to be? Well, I'm going to give you, the key is going to be the join attribute, the attribute that you're joining on. And the value is going to be sort of everything else, right? The rest of the tuple. And we can actually get away with removing this guy to save some space, but typically you wouldn't bother. Okay. So fine. So given a tuple that looks like this with 3 fields, we produce a key of 777777 and so on, and the value is the entire tuple, and so on. And again, notice that both the tuples from both relations are all lumped into the same input. All right. I may be belaboring this, but I want to make sure that's clear. Okay, so far we've done 2 tricks. One is lump everything together, and 2 is produce a key value pair where the key is the join attribute. Now, what happens in the magic shuffle phase? Well, everything with the same key gets lumped together, as we talked about, and so now you get a reducer invocation that has one reducer invocation for every unique key. So in this case, it'd be 1 for 999, so on, and 1 for 777, so on. And the list of values associated with that key will be all the tuples that share the same join key. Now, it doesn't matter what relation they came from, they'll all be in this list. So in this case, we get 1 tuple from the employee relation, and we get 1 tuple from the department relation. And here we get 1 tuple from the employee relation, and we get 2 tuples from the department relation. Right? And so now, in the context of a single computer, we have everything we need to compute the join. And further, each one of these reduce invocations can be done on a separate machine. Okay. And that's how we scale. So now this reduce function that the programmer would have to write if you're implementing a join phase would have to take this key and take all these tuples and produce the joined tuple, right? Where these 2 attributes came from employee and these 2 attributes came from department. And same thing here. Employee, department. Now, if you want to think about what kind of operation you need to implement in this reduce function, well, you've got a set of tuples from one relation, and you need to associate it with every possible tuple from the other relation, right? Because we know they all join. They're all, by definition, they all join. They all have the same key. They all match. So if you have every member of a set paired with every possible member of another set, if you remember, that's a cross-product operation. And so here again, we see relational algebra popping up sort of in a different context. Okay. So I don't want to confuse you too much, but the overall operation we're trying to do is implement a parallel join. It happens to be that locally, right here inside one reduce function, we recognize, aha, that's another relational algebra operator, a cross-product. But this is more for abstraction purposes than for algorithm purposes. Just want to point that out. All right. So again, you put on your relational algebra colored glasses and the whole world, these operators start to pop up everywhere. All right. So fine. So let's do this one more time just to make sure it's clear. So I'm giving you 2 relations, order and line item, and they have these fields: an order ID, an account, and a date. And here there's an order ID, an item ID, and a quantity. And we're going to join on order ID. So what's the map phase look like? Well, once again, the key will be the join key, in this case order ID. And the value will be this pair, the relation name along with the original tuple. And before we just sort of lumped these together in one tuple, and it doesn't matter very much. Here I've kind of structured it slightly differently, but the point is that all the information is here. The key must be the join key, and the value is the tuple as well as some sort of indicator of what relation it came from. In fact, maybe I'll ask real quick, why do I need that indicator of the relation? Well, in the reduce phase, I wouldn't be able to produce the joined tuples properly if I didn't know which tuples went with which relations. If I just had a big bundle of tuples and I couldn't really figure it out very easily, that would be a problem. Theoretically, you might be able to avoid tagging it explicitly with employee and department because you could deduce that, well, the employee table is the one that has a string first, followed by the join key, and the department relation has the join key followed by some other string. But it's a little dangerous to rely on that kind of information because you could be joining two tables that have exactly the same schema, and there wouldn't be any real obvious way to figure it out. So an explicit tag is a little bit safer here. All right, fine. So that's the map phase. Process we lump all the records together and produce key value pairs where the key is the join key from the corresponding relation, join attribute from the corresponding relation, and the value is the entire tuple tagged with the relation name. Okay. And there it is right there on the slide. Okay, so what's the reducer look like? Well, now we've got all the tuples that share the same key together, and it will produce these joined tuples. It will join this order tuple with both of these line item tuples to produce these two joined tuples. Okay. Fine. So now let's go on to a different example. And so here, maybe we're going to get started with analyzing a social network. So here we have a graph where every edge represents let's say a friend relationship. Or if you're thinking about Twitter, you could have this be a follows relationship. And so the input here is a set of edges with the semantics of Jim is friends with Sue or follows Sue, and Sue is friends with Jim or follows Jim, and so on. And so one point I'm making here is you'll notice that if Lynn points to Joe, then Joe points to Lynn, and so there's a symmetric relationship here. Okay. And I've done that for simplicity's sake to sort of avoid the confusion that can result from thinking about undirected graphs versus directed graphs. Okay. Fine. So anytime you see an edge going one way, you'll see the other edge coming back. Now, what we want to do here is, well, before I say what we're going to do, let me make sure the task is clear. We're going to count the friends. We want something very simple. We just want to say, how many friends does Jim have? And how many friends does Sue have, and so on. And so the desired output here is Jim with 3, because Jim has Sue as a friend, and Jim has Kai as a friend, and Jim has Lynn as a friend. And we want to have Lynn equals 2, or Lynn has 2 friends because Joe and Jim, and Kai is just 1, right here, Jim, and Joe is just 1, which is right here, Lynn. Okay. So this should already look like something we've already done before. So it happens to be social network analysis, and the records happen to be these pairs of people, but the algorithm you're going to use should start to stand out to you. Okay. And maybe you'll see why in a second if it's not clear. So in the map phase, how are we going to do this? Well, for every friend on the left-hand side, produce a key value pair where the key is the name of the friend, or the name of the person, and the value is just the number 1, indicating that there's exactly one friend associated with that. Sorry, exactly. That we've encountered one friend associated with, say, Jim in this case. All right, so this record gets turned into Jim in 1, and this record gets turned into Sue in 1, and this record gets turned into Lynn in 1, and so on. Okay, and then through the magic of MapReduce, the shuffle phase produces this intermediate result where we have Jim the key associated with a list of occurrences, 1, 1, and 1, and Lynn is associated with 2 occurrences, and so on. And then the reduce phase just simply adds up all these occurrences. And so what does this remind you of? Well, it's a lot like the word count example, right? Instead of documents producing words and counts, it's even simpler. It's for every record, just produce a single count for that for that person that the record represents, the person on the left-hand side. Okay. And after that, the reducer is literally exactly the same, right? It'll add up all the occurrences and produce a single number. Okay. So in the next segment, we'll talk about something a little trickier, which is implementing matrix multiplication in MapReduce. All right. Okay, so let's look at a simple matrix multiplication algorithm in MapReduce. So before we get there, just to remind you how to think about matrix multiplication, we've got a matrix with 4 columns and 2 rows multiplied by a matrix with 2 columns and 4 rows, and the output is going to have the number of rows from the first matrix and the number of columns from the second matrix, so it's 2 by 2 in this case. Okay, and again, just to refresh your memory here, what is this result? Well, it's the first row of the first relation, the dot product with the first column of the second matrix. All right, so it's 1.1 plus 3.4 plus 4.-3 plus -2.0, and that should equal 1. Okay, and so on. So that's, let's just say row 1 and column 1 dotted together gives you this position. Row 2 and column 1 gives you this position, and so on. All right, so I'm hoping that was intensely boring. All right, so in MapReduce, how do we want to do this? Well, what we're provided here is 2 matrices representing sort of a sparse matrix format. And a sparse matrix format is going to look like this. Okay, so this is row ID, column ID, and the value. And the reason I call this a sparse matrix format is that it would be inefficient to represent a very, very large matrix this way if you had a value for every position, right? So if you think about just a multidimensional array in memory, you don't have to be explicit about the I and j coordinates. You only have to provide the values. But if many of those values in that array are missing, then in this representation, I just can ignore them altogether. I just don't put them in, right? Okay. So anytime a value of 0, just remove that tuple altogether. Okay. So we're given 2 of these sparse matrices represented as tuples, sets of tuples, and we're going to do the same trick. Matrix multiply is a binary relation, and so we need to lump them all together. And we need to tag them with the source. And then we need to apply this kind of a trick. In the map phrase, for every element ij of A, emit several things. Emit a tuple where the key equals I comma k, and I'll tell you what k is in a second, and the value is value equals a I j. Now, we're going to emit one key value pair of this form for every k in 1 to n, which is what I've written down here. Now, what is n? Well, n is the number of columns in B, in the right-hand matrix. All right, so A is an L by M matrix, and B is an M by N matrix. So what is this saying? This is saying for every column of B, emit a tuple with key I to k, and value the value at ij. Okay. So I have a diagram on the next slide that explains this. But what you're doing is you're going to replicate this value to every column in B. Okay. And then for B, you do the same kind of thing. You say the key is going to be equal to IK, and the value is equal to B JK. Okay. And you're going to omit one of these key value pairs for every I, the upside down A for all I in 1 to L, where L is the number of rows in A, right? So you have to replicate the values of B to all the corresponding rows of A, and you have to replicate the values of A to all the corresponding columns of B. Okay, so this, and then finally in the reduce phase, you simply you can do the dot product and produce the output. So it may be hard to think about written out in notation like that. So think about this sort of diagrammatically. The first the value 1 1 in A needs to be sent. Actually, let me back up one step. First thing to recognize is that there's going to be one reducer per output cell in this algorithm. So here we're going to have 6 reducers. And if you had really, really large matrices, which is why we're playing this game, is to imagine that we have, 10,000 by 10,000 matrices. Sorry, matrix with dimensions 10,000 by 10,000. Then this starts to make more sense. So one reducer per cell in the output matrix. Okay, and think about what data does it need in order to compute its answer. Well, it needs, for the reducer 1 1 in the output, it needs all the values from row 1 in A, and it needs all the values from B1, from the first column of B, right? All those need to be sent here. Now, fine. So maybe I'll write that real quick. We need row 1 from A, and we need column 1 from B, right? Now, let's think about this second position. Okay, so this is row 1, column 2. Well, here we need row 1 from A and column 2 from B, right? So that's fine, but the problem is we don't have data represented in terms of rows and columns in the input. We have every individual cell. So we have to figure out where should this value, A11, be sent? Well, it needs to be sent to everybody that might need it, which means it needs to be sent here because we see row 1 from A. Well, this is in row 1 from A, therefore it needs to go here. And this second position is also involves row 1 from A. So this guy needs to be sent to 2 places, which is what I was trying to draw here with these colors. It gets sent, let me draw some more arrows here and see if it gets too cluttered, which I'm sure it will, but we'll try it anyway. It needs to be sent to both of those locations. So for every column of B, you need to have row this value be sent. And similarly for this guy, right? So to all the reducers that might appear in row that need the data for row 1, you need to send it to all of them. And so this is the reason I'm sort of belaboring this is that this is kind of a nice trick that MapReduce can do. Remember, you can replicate, right? You can send a single value out of the mapper to many places. And when I say send to many places, I don't mean literally sort of write it on the wire and send a packet across the network. What I mean is attach a value to multiple keys, and then every individual key will go to a different place, to a different reducer. Okay, and through this trick, we can sort of arrange for matrix multiply to occur, and this arguably scales pretty well, right? We've done some replication, but that replication is kind of necessary, and this whole thing can sort of happen in parallel. And then finally, again, each reducer produces the sum AI times BJ. Sorry, produces the dot product of a row of A and a column of B. Okay. So let's talk a little bit about what kinds of systems MapReduce is deployed on. So I don't spend too much time on the system internals, since this is a data science course, not a distributed systems course, but it's good to have an intuition for what's going on under the hood. So there's three types of systems to be aware of, or architectures to be aware of: shared memory, shared disk, and shared nothing. In these diagrams, these cylinders are the disk, these rectangles are the memory, and these circles are the processors. Okay. So shared memory means that every processor has access to all of the memory and all of the disk. And this is what you think about when you have sort of a laptop if it has 4 cores in it. If you have a quad core system, or nowadays if you have 6 or 12 cores in your laptop, this is the model that's being used. This is the architecture that's being used. Shared disk is somewhat less common in, at least in these contexts that we're talking about, although certainly common enough overall, where you'll have individual machines that all access a shared file system. Now that setup is very, very common, but for using that setup for parallel analytics is sort of the domain of high-end commercial databases. So your Oracles and your IBMs will often use a shared disk architecture. Okay. And then shared nothing is really what we're focusing on here. And this is what MapReduce is designed for, and what increasingly and largely parallel databases are designed for as well. Okay. And shared nothing here means individual machines that are only connected by a network. Okay. No shared memory, no shared disk. Fine. So the argument is that only the shared nothing architecture can scale to sort of thousands of computers and beyond. Okay. Because eventually that the sharing of memory or the sharing of disk eventually becomes a bottleneck and limits how many computers you can attach to the same device, or same logical or physical device. Okay. And so learning how to program these massive shared nothing clusters is what MapReduce and parallel databases are all about. And the shared memory machines are perhaps the easiest to program, but are conventionally assumed to be pretty expensive. I should point out that the costs are dropping fairly quickly, so it's getting more and more feasible to buy a pretty beefy machine with lots of main memory and lots of cores, and your problem might fit inside that one. So when you see people deploying Hadoop and MapReduce on fairly small clusters on the order of, say, 10 nodes, you should see whether the data sizes they're processing are actually all that large, right? It could be that the data sizes they're processing are something that fits in main memory on a similarly priced amount of hardware. Okay. So fine. So Hadoop and MapReduce are designed for really, really large clusters. Okay. All right. So this is the context we're in: a large number of commodity servers connected by a high-speed commodity network. And here, you think about a data center. There's a rack that has a number of servers, and there's a data center that has many racks. And this is how you organize your thousands or tens of thousands of computers. Okay. All right. So you're looking for massive scale parallelism that will run, jobs that will run for many hours, even on thousands or tens of thousands of servers. That's really the context we're in. So when you're in this context, an issue that comes up that does not come up all that often in a much smaller context is failures, right? So if you're running a job for a long time on thousands of computers, the chance of something going wrong during that job becomes essentially 100% probability, right? There's going to be something that fails. And so your system of processing, doing this sort of analytics, has to tolerate this kind of failure. You can't roll back to the beginning and just restart every time there's a failure occurs, or you would never get anything done. Okay. So even if the mean time between failure for, say, a disk is a year, if you've got 10,000 servers with multiple disks, or 10,000 disks, let's say, spread across 1,000 servers, or any combination hereof, you're going to start to have failures once per hour. And you can look up the mean times failure and actually do the math, but there's a couple of nice papers out there that I'll try to put in the readings if I remember. Okay. So failures are what we're concerned about here. All right, so that's hardware. Popping up the stack one level is this distributed file system, and you might see HDFS too, which is the Hadoop distributed file system. So you remember the context here was that MapReduce was proposed in a paper in 2004 by Google, and Hadoop was the implementation of the ideas in that paper. Okay, so we can almost use them interchangeably because the actual implementation at Google has certainly evolved since that paper and is not completely known, right? So when people are talking about MapReduce, they're typically talking about Hadoop or other implementations of the programming model that have nothing to do with sort of scale out. But shared nothing MapReduce can be assumed to be synonymous with Hadoop. Okay, so this is a file system for very large files, and the idea here is that if you're going to take a single file on your own computer, you can manipulate it as a single unit. But if you're going to take a very, very large file and put it on a file system that's on a cluster of machines, then there has to be some layer of logic that knows how to split that into pieces and put those pieces in different machines and keep track of where they are. And that's what this distributed file system software does. So each file is, as you're uploading this data to the cluster, each file is partitioned into chunks that are, say, typically 64 megabytes, although this is configurable. And so each chunk, and this is critical, is replicated several times, right? So there's not just one copy of the chunk. There might be multiple copies on different machines. Why? Because if one of them goes down, you want to have access to the other chunks, okay? And you want to make sure these are spread across different racks in case the entire rack of computers goes dark. You still have another copy of it, okay? And so the implementations here are GFS and HDFS. DFS is the concept, and the implementations are GFS and HDFS. All right, so here's the phases of MapReduce that's a little bit more detailed than the abstract phases that we were talking about when we were talking about the programming model. Okay, so there's a file split here that's read from HDFS, and remember HDFS means it's replicated. There's the chunks could be, there's multiple copies of every chunk, and there's a unit of code called the record reader that breaks that chunk into, I'm using chunk and split sort of synonymously. I'm not a big fan of the term split because it's sort of sounds too much like a verb to me. The record reader parses that splitter chunk into individual records. Then the programmers, the user's map function is called on that individual record. And then there's a step called combine that we haven't talked about, but I'll talk about in a moment. Next, actually. Okay, and then the output of these phases are written out to local storage on that node, as we said. So then these regions in local storage, one per key, are pulled across the network by the reduce phase. Then all the regions from all the different map tasks that correspond to the same key are sorted together in parallel. And finally, the user's reduce function can be called to produce whatever output it produces. And then the output of that step is actually written back out to HDFS so that it's replicated. So again, if something goes wrong in the map phase, you have to rerun the mapper. And if something goes wrong in the reduce phase, you have to rerun. You can pull the output from the local storage from the map phase. And if something goes wrong in the overall job, you're safe because you don't lose data because the HDFS are replicated. And if you lose a reducer and you lose corresponding mappers, that's fine. You can sort of rerun whatever you need to rerun. Fine. So the point is that you're guaranteeing for fault tolerance during job execution. All right. And so let's talk real briefly about the combiner. So to think about why we need a combiner, go back to this word count example that we began with. Well, in each case we produced a word and just the number 1. In the earliest version of this, we just produced the number 1. Right. Sending all of these occurrences of word 1. So if word 1 appeared twice, then you're going to get a key value pair with W1 and a number 1 and another occurrence of W1 and a number 1. And you're going to send both of these guys
across the network to be sorted in parallel and grouped in order to be processed by the reduce. Well, that's sort of wasteful. You'd like to combine these into a single record, W1, comma 2, and then just send that because it's smaller. Well, you could rewrite your map function to do this, but it's such a common need that you have this capability called a combiner. And so a combiner identifies key value pairs with the same key and lumps them together before sending it over to the reduce side. So it just saves the network traffic. In many cases, the combiner function can be literally the same function as the reduce function. It all works out. And what needs to be true for this to work is that the function that you're applying needs to be associative and commutative. But I'm not going to say much more about that. Okay, so here's what it looks like in pseudocode. We saw the map function earlier, and we were emitting this key value pair of a word and a count. And we saw the reduce function earlier. But what we're adding new is a combiner function that has the same type signature as a reducer. And again, often in many cases can literally be the same implementation as a reducer. And the only point of this is that it's being applied before sending data across the network. Fine. So here's sort of a summary of a Hadoop job that I like a lot, and this is from a Huivo who's now at NYU Poly, I believe. He's still at NYU Poly. So the data begins on HDFS, and there are these chunks, and the in-part partitions go to map tasks. Now these are, again, not invocations of the map function. These are entire tasks. And the map, each individual map invocation may produce multiple key value pairs, but regardless, the map task almost certainly does, right? So it's going to produce these local sort of colored key regions. And the regions are going to be pulled across the network to the reduce servers. And here in this example, there's only 2 reduce servers. Now, before we gave this example, we sort of showed all the blue ones going together and all the red ones going together. That was a bit of a simplification. What actually is going to happen is that if you only have 2 servers, well, all the hundreds of possible keys need to be mapped to just those 2 servers. So you're definitely going to get a mix going to the same place. And this is where we've been a little bit glib up until now. We've said that you specify the key and it hashes to a particular reducer, which is true logically, but before that, you have to actually get it to a machine where lots of reduce tasks might be running, or lots of reduce invocations might be running. Okay, and so, in this case, the blue guys and the red guys both ended up on the same machine, and the green guys and the orange guys both ended up on the same machine, and then this parallel sort manages that, right? So it puts all the red things together and puts all the blue things together, and then for each individual color, one reduce invocation is called. Okay, and the reduce function is called, and it produces the output partition, and then that output is then written back out to HDFS. Okay. Let me stop there, and I'll pick up here and talk a little bit about parallel databases and how they do query processing, with the point being that it looks a lot like MapReduce. Okay, so let's talk a little bit about other large-scale data processing systems besides MapReduce. And as a step to that, let's think about the design space of possibilities here. And so this is a breakdown that was proposed by Michael Lazard, who's developed a system called Dryad at Microsoft, which is a very nice system with the same sort of motivations as MapReduce. Okay, and so he divided this space into these 3 axes, where you're worried about sort of low latency, very interactive sort of speeds, quick turnaround time, versus things that maximize kind of throughput, massive batch jobs operating on thousands and thousands of computers at once, versus another axis here is sort of whether it's in a private data center or whether scaled out widely across the internet. And then maybe the third axis is data parallel versus the shared memory, okay, that we talked about. So the areas that we're mostly concerned with are going to be here, which is what we're talking about currently, and then in a couple of segments we're going to talk about these low latency, smaller operations, which you can think of as the NoSQL systems. Okay, and then maybe where Michael placed older relational databases, although he didn't label it the same way I have, is down here in this quadrant where they're mostly in shared memory sort of space and low latency. I say older databases to try to point out that not all relational databases operate in that space. Many are, most in fact, most parallel databases are data parallel as well. And so this is, MySQL and PostgreSQL, if you're familiar with those, are probably in this space. Shared memory, shared disk. All right, and here HPC means high performance computing, where it's a private data center and it's a big, massive shared memory. But it's a batch job submission system, right? You say you run your big compute intensive job and submit it to the machine, and it processes on it and eventually returns the results. And then I'm not going to talk too much about this, but this notion of grid computing was really sort of focused on connecting up clusters of computers from different universities and letting them all sort of talk to each other. And so that's why he's pushed this up in this other axis. Increasingly, you're seeing these systems also being pushed up in this axis. Internet scale, planetary, distributed hash tables with different kinds of layers for guaranteeing certain kinds of semantics. So the spanner system from Google fairly recently is a nice example of this. Okay. So, sort of wrap up what we talked about last time. Large-scale data processing, many tasks need to process big data and produce big data, and so you want to use hundreds of thousands of CPUs and hundreds of thousands or tens of thousands of computers to solve these problems. But this needs to be much easier, and so there are such things as parallel databases. We talked about databases, and we sort of extolled the virtues of programming in that model. And they exist, but they're often expensive. Well, they almost exclusively are expensive, and they're difficult to set up. And it's actually not totally clear that many of the parallel databases scale to really hundreds or thousands of machines. Okay. And so MapReduce came around at a time as a bit of a response to this scenario. So it's more of a lightweight framework featuring automatic parallelization distribution, as we've been talking about, featuring fault tolerance, and I mentioned a couple other things here that are perhaps less important, but the I/O scheduling, the status, and monitoring. So really sort of strip everything down to just parallel processing, not all the features that parallel databases offer, just parallel processing with the added benefit of fault tolerance. Okay, and this really seemed to scratch an itch with people. I'll argue here, and I'll probably mention this again at some point, that it's not totally clear to me that MapReduce would have been quite so popular had there been available a parallel open source relational database product. But all the open source databases were all not parallel. In fact, they were even single-threaded for query processing. Only a single thread was working on an individual query at a time. But that's speculation. Well, actually, I have a little bit of evidence for that I'll lay out for you in a bit. Okay, so now I want to talk about, I guess I'm building up to that argument. I want to talk about parallel databases and how they work, and hopefully show that there's some similarities, show where there are similarities and where there are differences. Okay, so recall that a key idea of relational databases was this notion of a relational algebra, where you could write sort of plans like this, and that this top-level language called SQL was the most common way of producing a relational algebra plan, right? You wrote a query in SQL and it was automatically turned into a relational algebra plan by the system. Okay, so this is kind of thrown out the window with MapReduce, arguably in favor of sort of flexibility and providing the programmer more control. But let's go back to this model for a bit. Fine. So now we want to evaluate these queries, but we want to do it in parallel now. And so there's two different terms that I want you to be familiar with. One is distributed query and one is parallel query, or distributed query processing and parallel query processing. And so they're both ways of sort of taking advantage of more computing resources for the same query, but they behave a little differently. So in a distributed query, what you're doing is taking a single large table and distributing it across a cluster, just like we talked about, and then you're breaking your query into individual pieces to operate on each of those partitions of the file. Okay, so this sounds like, well, isn't that basically just the same thing as MapReduce? It is, except for the fact that all the results of those individual pieces are all sent back to the head node, to a single server to sort of finish processing. So for example, if you're doing a count, right, you want to count all the records that match some criteria. Well, if you have a very large file that's split across several machines, these distributed query systems, Microsoft SQL Server in particular is an example of this, is smart enough to break the query into a bunch of little pieces and run each of those pieces in parallel. But as they start to stream tuples out to be counted, they'll send them all back to the head node. Actually, I guess that may not actually be true, because it may be smart enough to figure out that you can just count things in parallel and add them up. But it's not hard to construct a query where you have this bottleneck of sending everything back to a single server. So it's essentially, you can think of it as like having the map phase, but not really the reduce phase. Now, parallel query, every individual operator in the relational algebra is implemented in parallel. So when you're doing joins across a bunch of nodes. When you're doing groupings, you're doing groupings across a bunch of nodes. And we've seen how to implement a relational join in MapReduce, and it is not too far off from how it's actually implemented inside databases. Okay, so if we know how to implement join, that's usually the harder one. Trust me that you can implement the other ones that way. Well, now we have a way to do parallel query processing with the relational algebra. So why not do that? Well, the answer is people do that, and we'll come back to that in 1 second. Okay, so for a distributed query, I guess I was waving my hands a second ago trying to explain this when it was on the next slide. You can imagine constructing a view, and we've talked about views. If you don't recall what that is, it's a named query that can then be accessed as a single table. So we say that the sales table is really the union of a bunch of smaller sales tables, one for each month. And in particular, you could put each one of these sales tables on a different disk, or even a different server altogether. Right? And then the user who's querying the sales table doesn't have to care about the fact that this is actually a distributed table. They don't have to go gather up all the results from January and then gather up all the results from February and then gather up all the results from March and put them all together. That's done automatically by the system. However, right, and so this is the create table statement that we didn't talk about for constructing the sales table for individual March. Okay, but again, however, when you process this stuff in parallel, that works great. But when you get the results, you need to send them all back to the single node to finish processing, and that's the limitation of distributed query. So it's great that you get some parallelism, but it can't do everything in parallel, and you can see this when you run performance experiments. But a true parallel query example would be, for example, from a system called Teradata, which is a database company that many folks haven't heard of because they've been selling very, very high-end databases to very, very high-end customers, and so they don't sort of need to have much word of mouth in the popular news media. But what's happening here is that as every individual row is inserted into the parallel database, it will be assigned to some particular server using a hash function. Okay. Fine. So everything is automatically partitioned more or less randomly across the cluster. And then whenever you're running queries on this, all the machines will access their data in parallel. Okay. And you can see this has a little bit of the flavor of how we did the relational join in MapReduce, and that should become even more clear in a second. Okay. So remember, this is our query, orders and line items, and this is the plan that we're going to do. We're going to select some orders and then join the orders with the items. All right. So how this starts is these parallel processing units called amps in Teradata terms will each contain a piece of the data, a chunk of the data, and the chunk was defined sort of randomly by hashing. Okay. And so they all in parallel should begin to scan their individual chunk, and then they'll all in parallel apply the filtering condition to throw out certain records that they don't want. And then they'll all in parallel hash on the, actually this isn't right, this should be hash on the order ID. not the item ID. So this is the join key, right? We're going to join on order. And I probably got this wrong back here too. Yeah, this is wrong as well. This should be join on order ID. It doesn't quite make sense to call this item. Same thing here. Okay, so then the all in parallel hash on the join attribute, the order ID, and that will shuffle it, for lack of a better term, to another set of amps, perhaps the same set of amps, but typically another set of amps that will do the next step, actually compute the join. And so this should look a lot like a MapReduce job, right? You've got a map function that's scanning and selecting, and actually then hashing, and then we got a reduce function coming up to actually produce the join. Okay. And for the other relation, the same thing happens. You scan the items and then hash on, again, this is order, order, order. All right, so you're scanning scanning and selecting on the orders and just scanning on the items, and then both are hashed on the appropriate join attribute. And lo and behold, all the items and all the orders that correspond to the same order ID, to the same join attribute, same join key, end up on the same machine, and you can actually process the join, just like the MapReduce example we saw. All right. So then at the end of these two steps that I've shown you, AMP4 will have all the orders and all the line items where hash of order, goodness, equals 1. And this AMP5 will have all the orders and line items where hash of order equals 2. And this one will have all the orders and line items where hash of order equals 3. And now it has enough information to individually and in parallel finish the join and actually produce the result. And all these ought to be orders as well. All right. So fine. So the point is that the same machinery already exists in these parallel databases. And in MapReduce, if you're interested in doing a join, you're sort of implementing this yourself. And so this observation was not lost on people that, hey, it might be nice if there was sort of a standard way of doing join in MapReduce and we didn't have to sort of rewrite it ourselves every time. And in fact, there's libraries on top of MapReduce that do this. And so there's a library called Pig from Yahoo that I encourage you to check out that is recognizably relational algebra, right? There are operators called join. There are operators called group by. It does have a bit of a funny data model where you're allowed to have kind of complicated nesting as opposed to just straight tuples and straight relations. But the relational algebra is there. And in fact, this is sort of one of the points I want to make is that it's important to sort of be able to modularize the concepts that come out of various communities and especially databases. It tends to be true that it's kind of all or nothing. If you're interested in using databases, well, then you have to take everything. You have to take the whole package. It's all or nothing. But increasingly, what you're finding is that these concepts are leaking out into other systems, which is why I'm really emphasizing this relational algebra piece a lot. Is that you can use these concepts independently of buying into a strict relational model. Okay, and certainly not a strict adherence to a particular implementation of it. Now, another system called Hive is literally SQL on top of Hadoop. So it goes one step even higher. Instead of just stopping at the relational algebra level, it actually provides a SQL interface. Impala is a more recent system from Cloudera, I should mention here. Cloudera, by the way, is a company that has aligned themselves pretty closely with the Hadoop stack, and so they have their own fork of the Hadoop system and a bunch of great tools for working with that ecosystem. And Impala is a new system that they produce that provides SQL over HDFS and actually uses a lot of the code from the Hive system. Okay. Cascading is another system that's maybe a little bit less common, but it's also very recognizably relational algebra. The Dryad system I mentioned has nothing to do with MapReduce directly, except for a similar motivation, but it very obviously has relational algebra there. The Clystera system I mentioned, it's more of a research project, and it's not clear to me that the code is available, but it's also very clearly relational algebra. So, when you put your relational algebra goggles on, you start to see the world in this way, and it starts to come up everywhere. Okay. So it's good to go back and understand those operations. Okay, so I want to spend a little bit more time on the details of MapReduce versus relational databases beyond just the sort of how the query processing happens. We saw that parallel query processing is largely the same. Many of the algorithms are sort of shared between them. There's a ton of details here that I'm not going to have time to go over. But the takeaway is that the basic strategy for performing parallel processing is the same between them. But there's other features that relational databases have, and I've listed some of them here. So we've mentioned declarative query languages, and we've mentioned that those start to show up in Pig and especially Hive. Now there's a notion of a schema in a relational database that we didn't talk too much about, but this is a structure on your data that is enforced at the time of data being presented to the system. So any data that does not conform to the schema can be rejected automatically by the database. This is a pretty good idea because it helps keep your data clean. It's not real feasible in many contexts because the data is fundamentally dirty, and so saying that you have to clean it up before you're allowed to process it just isn't going to fly, right? And so this is one of the reasons why MapReduce is attractive, is it doesn't require that you enforce a schema before you're allowed to work with the data. However, it doesn't mean that schemas are a bad idea when they're available. And in fact, really, even with MapReduce, a schema is really there. It's just that it's hidden inside the application, right? So when you read a record, you're assuming that the first element in the record is going to be an integer, and the second record is going to be a date, and the third record is going to be a string. So that schema is really present. It's just present in your code as opposed to pushed down into the system itself. And there's a lot of great empirical evidence over the years that suggests it's better to push it down into the data itself when and where possible. And in fact, you're starting to see this. So Hive and Pig, again, have some notion of schema, as does DriveLink, as does some emerging systems. There's a system called Hadapt that I won't talk about really at all, but combines sort of Hadoop level query processing for parallelism, and then on the individual nodes, there's a relational database operating. And one of the reasons, among many, is to have access to schema constraints. Fine. Logical data independence. This actually you don't see quite so much. So this is the notion of views, right? Does the system support views or not? And you haven't seen quite as many instances of Hadoop-like systems that support views, but I predict they'll be coming. Indexing is another one. So we talked about how to make things scalable, that one way to do it is to derive these indexes to support sort of logarithmic time access to data. That's not available in vanilla MapReduce. Every time you write a MapReduce job, you're going to touch every single record on the input. You're not going to be able to zoom right in to a particular record of interest. That's wasteful, and it was recognized to be wasteful. And so one of the solutions, you see people adding indexing features to Hadoop, and HBase is an open source implementation of another proposal by Google for a system called Bigtable that, among other things, provides kind of quick access to individual records. And HBase is designed to be sort of compatible with Hadoop, and so now you can design your system to get the best of both worlds. Okay, so you can get some indexing along with your MapReduce style programming interface. And once again, I'll mention Hadapt here as well. One of the motivations for Hadapt is to be able to provide indexing on the individual nodes. Okay. Fine. So I'll skip caching materialized views. So this is the same thing as logical data dependence, except you can actually pre-generate the views as opposed to evaluate them all at runtime, but we're not going to do too much about that. And then transactions, which I'll talk about in a couple of segments in the context of NoSQL. But while databases are very good at transactions, they were thrown out the window among other things in this kind of context of MapReduce and NoSQL, and they're starting to come back. Okay. But remember, what MapReduce did provide was very, very high scalability. So this is, thousands and ups, 1,000 of machines and up. And it also provided this notion of fault tolerance. So relational databases didn't really treat fault tolerance this way. They were unbelievably good at, recovery, right? If you were, because of this notion of transactions, if you were sort of operating on the database and everything went kaput, given some time, it would figure everything out and recover, and you can be guaranteed to have lost no data. Okay. That's fine, but that's not the same thing as saying during query processing, while a single query is running, what if something goes wrong? Do I always have to start back over from the beginning or not? And sort of the implicit assumption with relational databases was that your queries aren't taking long enough for that to really matter. But in the era of big data, of massive data analytics, of course you have queries that are running for many, many hours, right? And so having to restart those, and of course they're running on many, many machines where failures are bound to happen. And so that context is something that MapReduce sort of really motivated. And now you see modern parallel databases capturing some notion of fault tolerance in general. Okay. So this is sort of a list of some partial list of contributions from relational databases, and this is a partial list of contributions. Well, maybe a complete list of contributions from MapReduce. And my point is that you see a lot of mixing and matching going on. The design space is being more fully explored. It used to be sort of all about relational databases with their choice in the design space, and then MapReduce kind of rebooted that a little bit, and now you see kind of a more fluid mix. People sort of cherry picking features. Okay, fine. And then the last one I guess I didn't talk about here is what I think was really, really powerful about MapReduce is it turned the army of Java programmers that are out there into distributed systems programmers, right? A mere mortal Java programmer could all of a sudden be productive processing hundreds of terabytes without necessarily having to learn anything about distributed systems. That was really, really powerful, right? When the analog in databases was, I mean, you had to become a database expert to be able to use these things. Okay. And so I think that impact is hard to overstate, right? The ability for one person to get work done that used to require a massive team and 6 months of work was significant. All right. Okay, so just to wrap up this discussion of MapReduce versus databases, I want to go over some results from a paper in 2009 that's on the reading list where they directly compared Hadoop and a couple of different databases and see if we can maybe explain what some of these results tell us. Okay, so this was Andy Pavlo and some other folks at MIT and Brown who did an experiment with this kind of a setup. So the comparison was between three systems: Hadoop, Vertica, which was a column-oriented database, and DBMS X, which shall remain unnamed, although you might be able to figure it out. And so we haven't learned what a column-oriented database is and what a row-oriented database is, but we may have a guest lecture later that will describe that in more detail. But for right now, for the purposes, just think of these as two different kinds of relational database, or two different relational databases with different techniques under the hoods, under the hood. Okay, and so there's two different facets to the analysis. One was sort of qualitative about their discussion around the programming model and the ease of setup and so on, and the other was quantitative, which was performance experiments for particular types of queries. Okay, so the first task they considered was what they call a grep task, and so this is a task to find a 3-byte pattern in a 100-byte record. And the data set was a very, very large set of 100-byte records. Okay. So this was done this task was performed in the original MapReduce paper in 2004, which makes it a good candidate for a benchmark. And so the data set here is 10 billion records with totaling 1 terabyte spread across either 25, 50, or 100 nodes. Okay, so you're just trying to find this record. So this is much like this genetic sequence DNA search task that we described as a motivating example for sort of describing scalability. Okay. Fine. So what were the results? Just to load this data in, this is what the story sort of looked like. Hadoop and the system called Vertica, that they're really the theme here is they were the designers of the Vertica system. And so most of these results are going to show Vertica doing quite well for a variety of reasons. So we're not going to talk too much about those particular reasons. We're mostly going to be thinking about DBMSX, which is a conventional relational database, and Hadoop. Okay. So here, loading is fast on Hadoop, while loading is slow on the relational database. And again, it was sort of fast on Vertica as well. So why is it faster on Hadoop? Well, there's not much to the loading, right? You have to put it into this HDFS system, so it needs to be partitioned, but that's about it. When you put things into a database, it's actually recasting the data from its raw form into internal structures in the database, and that takes time. Okay, and the process could be even worse because if you're building indexes over the data, you actually, every time you insert data into the index, it needs to sort of maintain that data structure. Okay, and so load times are known to be bad. So the takeaway here is remember that load times are typically bad in relational databases relative to Hadoop because it has to do more work. Now, once it's in the database, you actually get some benefit from that, and we'll see that in a second even in these results. But it's actually, we know that it conforms to a schema, for example. Hadoop is just a pile of bits. We don't know anything until we actually run a MapReduce task on it. Okay. And so how much faster? Well, in their experiments on 25 machines, we're up here at 25,000. These are all seconds, by the way. 7,500 seconds versus 25,000, and a little bit less as we go up to more servers. Okay. Now, actually running the grep task to find things, this is what we see. Again, maybe ignoring Vertica for now because I haven't explained to you what the difference about Vertica is that allows it to be so fast. But just think about a relational database from what we do understand. Hadoop is slower here, and the primary reason is that it doesn't have access to a index to search. Okay. So again, no index is available. Hadoop has to do that's wrong. Okay, so Hadoop is slower than the database, even though both are doing a full scan of the data. The grep task here is not something amenable to any sort of indexing. You actually have to touch every record, so there's no fundamental reason why the database should be slower or faster. But partially because it gets a win out of the structured internal representation of the data and doesn't have to reparse the raw data from disk like Hadoop does. And so I said there's no fundamental reason. There is a fundamental reason because it's already in a kind of a packed internal binary representation, which we paid for in the loading phase, but now we get the benefit from here in the query phase, even before we even talk about indexes. Okay. Now, a selection task where you're not having to scan every record necessarily, that is amenable to indexing, as we discussed in the scalability segment. Well, the story is even more extreme, right? The Hadoop results are just way, way, way higher than both the database and in particular the Vertica results. And so here, the reason is because you can build an index on the PageRank attribute and zoom in directly to the records that you're interested in. Okay. Fine. So those are sort of search and retrieval tasks, arguably not exactly what Hadoop was designed for. Hadoop was designed more for analytical tasks. So now consider these. So here the data set is 600,000 HTML documents, which works out to be about 6 gigabytes of data per node. Along with another data set is 155 million user visit records and 18 million rankings records. So this is kind of a web data processing task. All right. And so a simple aggregate task here is to add up all the ad revenue corresponding to a particular subdomain. So they apply this function substring to the source IP to pull out the first 6 characters, right? The subnet mask of the first prefix of the IP address, group by that, and just add up the ad revenue. Okay, so this is one thing to point out is it's actually very nicely and simply expressed as a SQL query. You don't necessarily have to write a bunch of Java code in MapReduce to express it in this particular case. Okay, and so here are the results. Again, you see a row-oriented database beating Hadoop, and the reason here is maybe not quite so easy to explain, but essentially it's the internal representation in the database. Again, wins credit. There's no parsing that has to happen. Okay. On this same schema, there's a join task, which is to find the source IP that generated the most ad revenue along with its average page rank. And so this is kind of a complicated thing involving multi-step, multiple passes over the data, to sort of compute the average page rank and then find the source IP that, find the maximum ad revenue, find that corresponding source IP, and then compute its average page rank. And so the implementations here are a fairly complex SQL statement involving the use of temporary tables. And in MapReduce, it has to be 3 separate MapReduce jobs chained together. Okay. And so for the complicated SQL, we won't go through this in too much detail, but just notice that there's a join, and then there's a group by. We looked at some complicated SQL, and we sort of showed how to break them down, and this is no different. So there's you see 2 tables, which you should think to yourself join, and then you see a group by, and so those are really the 2 tasks going on. And then the second step is to do a big sort, because you see the order by, and just find the topmost record. Okay. Fine. A join and a group by. And so here the results are also pretty impressive. And the reason is, again, because of the indexing, right? This join can be done very, very quickly because there's different kinds of ways to do the join. The one we described for MapReduce is when you have no information about the schema. All you've got are these 2 big relations, and you have to scan them both in parallel and shuffle them across the network with respect to the join key, and then perform the join. But if one of them is indexed on that join attribute, you have other plans available to you, and the database is automatically going to figure out the right one thanks to the magic of relational algebra. And so that's what's going on here. And so both Vertica and the relational database can do a lot better. Okay. Now, so that's fine. So that sort of paints the picture that maybe relational databases are great, and boy, this MapReduce framework is all wet, and why would anyone use it? Well, we talked about fault tolerance, but a couple of other things. There's other ways to avoid sequential scans that you can actually implement directly in Hadoop. So for example, if you have a large relation and a small relation, one thing you can, and the relation is small in the sense that it fits on a single node. It doesn't need to be partitioned anymore, which happens a fair amount. You could actually broadcast that, make a copy of it, and send it to every machine in the cluster, or at least every machine that has a copy of the other relation you're joining against. Right? So you're joining R and S is small and R is big. We'll just copy S to every partition of R, and now you can do the join locally without having to do this sort of shuffle phase. Okay. And so they didn't get a chance to take advantage of that mechanism. Moreover, there are, especially in modern systems, this paper was in 2009, which is now a little bit old, or quite a bit old, there are ways to provide indexing capabilities in a Hadoop stack. And so you're not sort of dead in the water when you aren't allowed to use indexing. So the positive view, if you look sort of warmly on this work, you can think, great, relational databases have all these benefits, and Hadoop can't really compete on some of these very basic queries. Another way of looking at this is, well, these tricks that we already know work really well, like indexing, do indeed work, and so all we got to do is add those to Hadoop, and we'll get the same kind of benefits. Okay. So what's interesting here is to read about the response from Google when this paper came out, which was a discussion published in CACM. And one of their points was that the largest known database installations were both at eBay at the time, which was a Greenplum on about 100 nodes, and a Teradata system on also about 100 nodes. And the largest MapReduce installations at the time were way larger, right? Nearly 4,000 at Yahoo and 600 plus at Facebook. And again, this is years ago. So these numbers are much higher actually in both cases. But I think the overall point is still the same. The size of even perhaps typical Hadoop cluster is pretty enormous. Okay. To conclude the comparisons, we've said this a couple of times, but just to wrap it up one more time, what can MapReduce learn from databases, in the words of the authors of this paper, is that declarative languages are a good thing, schemas are important, and what can databases learn from MapReduce is this query-level fault tolerance, support for what I'm calling is in situ data, which is data as it lies, right? Supporting don't require that the data be sort of transformed and loaded before you can work with it. And then maybe embrace open source, because if there had been an open source parallel database available, you might not see the same popularity in MapReduce. Okay. Other systems that have been considered in the same kind of framework after the fact were HadoopDB, which became Hadapt, which I mentioned, is now a startup, and this is Hadoop file system, but has it's actually not Postgres anymore. It's MonadDB. But the point being, a relational database on individual nodes in order to get some of the indexing and some of the at least local level benefits of relational query optimization. And then Hive also came out since then. Fine. So that's the end of MapReduce of both MapReduce itself and MapReduce compared to relational databases. And in the next segment, we'll talk about NoSQL systems that are solving a slightly different problem.